Let's continue the discussion. So, previously we started with the runtime leakage reduction. So, the runtime leakage reduction techniques are VDD scaling, dual VTH assignment approach, and dynamic VTH scaling. So, the VDD scaling we seen like as as we are going to use the different VDD for different circuits. So for that we said something like two things we said. So even if you are reducing the VDD, very important thing, the GIDL and the DIBL table will get reduces. So once it get reduces, then so now we'll see about the next technique is nothing but a dual threshold CMOS technology, or we may call this DT CMOS. Sometimes we may call like that. Okay, now what will be in this dual threshold? That is a two different threshold. We are going to use the CMOS technology. That is low VTH. The other one is high VTH. When we use this, so what will happen? When you are going to use the low threshold voltage, what will happen? The delay will be, or delay will get reduces. When you are using a high VTH, then delay will be increases. It increases the delay. So what you have to do in the sense, see, you are having a one circuit example. Okay, this is the some example circuits actually. Some set of circuits we are having here. Now what you have to do, we need to assign low VTH. Which circuit you have to assign the low VTH to the critical path delays. You may ask, what is the critical path? Critical path gets. The critical path is nothing but it is a worst path. The critical path is nothing but worst or longest path, I can say. Longest path from input to the output. That is only we can call it as critical path. The critical path is nothing but it's the longest path. So the maximum the time delay which will take from the input to the output, the maximum time which path is taking. So that here is specified here in this diagram with the colors, with the black color. See this? So like which is the path here in the sense, see the path is like this. This is the critical path accuracy. We are going to trace the path. Okay. So now in this, I can say in this diagram, whichever I am showing, the black color whichever we are showing, our nodes are in the critical path. So this will be a low. Which one? This will be here. This the black colors are specified. No, this is low VTH we have to use. Next, the nodes which are having in the this one, the white color one, this one, the non-shaded gates. These are all with the low VTH. So keep it in our mind. Nodes in critical path also should be low VTH, even here also, because sometimes so the low VTH transistors in a critical path will for the higher performance actually. So that is why I said, right, that's all low VTH transistors in a critical path, because rest of things will be fine. This transistors only, or these gates I can say only these gates, the darker gates are the critical path. That will take much time. So we need to use the low threshold voltage for that. Now when you use in this way, the rest of the gates, what you have to do, you have to use the high VT. You have to use example, I will say example, this is the example just let me take. Okay, high VT, that is 0.25, threshold voltage is 0.25, is assigned to all the gates. Assigned to all the gates to of the critical path. Okay, because 0.25 is nothing but what? 0.25, because as you know, the threshold voltage range is 2.3 less than the threshold voltage, right? This is threshold voltage 0.2 VDD to 0.5 VDD, means when you're having the range from 0.5 VDD up to that value will be low VTH. This already we seen. More than that value, less than more than 0.2 VDD, less than 0.5 VDD will be treated as high VTH. Okay, so that is why what we done in this. Now what we will do, we need to increase the threshold voltage for. Now what we will do, now increase the high VT, increase the high VT to 0.96. Okay, 0.96 is assigned. So some of the gates, some gates is off in critical path. Now if you do in this way, see the below diagram compared to the top diagram, you can see here, you can see the critical path. Some of the gates are off. See, that is why I said here total 3 are there. This will be your black color is nothing but your low VTH. This is low VTH. Then this white color what we are showing, even this also low VTH. Then what we are having, this is high VTH. So now we can say if you do in this way, it will be assigned to some gates in the off critical path. When you do in this way, what we can do, we can reduce the leakage power. You can see this, still the example we are showing here, 0.396. Again we are assigning the 0.46 high VTH we are assigned to some gates in the off critical path. Now you can, if you compare with the simulation results and all, you can see this. Previously for 0.396 when you assigned, see here this has example I'm saying, this as high, correct, and this is actually, but now when you see here, you see this as low. It is depends on how the trial and error we have to do. That is what we can say here. So keep on, we increase from the low VT to high VT. So it is we have to use properly the lower threshold voltage where exactly is required. So for that, what when you are going to design a circuit, we need to find out the critical path first. And as soon as you found the critical path, then what you will do, the rest of the gates will be on offer. So you need to apply a little bit high threshold voltage, keep on increase, and you have to check the leakage power. Next is, you can say, the dual VTS assignment problem. You see that dual VTS means dual threshold voltage. Okay, when you are assigning, what is the problem we will face? See here we are saying the x-axis nothing but your the threshold voltage. This y-axis nothing but runtime leakage power. Okay, you can see here we are applying the VDD is equal to 1 volt. Then the effective gate length is 0.2 micrometer. Then effective the width of PMOS is 10.5 micrometer. The effective NMOS width 3 micrometer. The oxide thickness is 9.8 nm. These are the some parameters we are using here. Now you can see as the threshold voltage decreases, you can see this, as the threshold voltage decreases, what happened here? Your runtime leakage power is increases. See this? Then VD is equal to 1. So from this we can see the observation like not all the gates in not critical path can be assigned high VT. That is what. So no need to assign high threshold voltage to all the gates. Only selectively, only selective gates only we need to assign. That is why we are saying that is like the dual threshold voltage will achieve the best leakage saving under the performance constraints. So we need to select properly the threshold voltage, the low and the high, then we need to make a workout. So based on that also we can reduce the leakage power reduction, that is the runtime leakage power reduction. The next is the technique is called as dynamic VTH scaling. That is a dynamic threshold voltage scaling. If you see here, you can have like we'll have some workload. See this one. This I can call this the workload. Okay. Now you can see the workload is considered as this is 100%. This is 0%. Okay. This is will be very linear. This will be linear for which one in the sense? This is for only for frequency scaling actually. It's linear frequency scaling. But when you go for dynamic voltage frequency scaling, then it will be like this. So this will be your dynamic voltage frequency scaling. So what is happening here, like first thing is I want to say here, when you reduce the frequency, when you reduce the frequency, then we need to reduce the voltage also. Second thing is we need to reduce the power supply, that is VDD. If you are reducing the VDD, what will happen? The delay will be increases. This already we know. When you are reducing the power supply, delay will be increases. Then when you go for increasing the threshold, when you increase the threshold voltage, then delay will be increases. When you increase the threshold voltage, delay will be increases. So from this I can say for lower frequency, for lower frequency, for a lower frequency, right? The reducing frequency. So increasing the threshold voltage to match with the, you need to increase the threshold voltage to match the low frequency, actually to match the low frequency. Match the low frequency. So from this we can make a derivation of like reducing the frequency, then increasing the threshold voltage, then circuit will assist. Now how we can control the threshold voltage? How to control the threshold voltage? We can control the threshold voltage, by using, which method we can use actually? By using the body bias. Earlier we studied, right? Using the body bias we can able to control the biasing voltages. Next further I can say second method. These are the methods how we can control, how to control VTH. Okay, how to control VTH. One method is we can control the VTH by using the body bias. Next thing is we can use the charge pump. That is one circuit actually. It's a charge pump circuit called, or voltage pump. The charge pump will increases the reverse bias. Okay, using the charge pump circuit you can increase the reverse bias. Automatically you can able to control the threshold voltage. Even that also I can say. The next thing is you can say we can operate with the two different frequencies also. Operate at frequency 1 on the threshold voltage 1, then we can operate that with the frequency 2 VTH 2, threshold voltage 2. Two different frequencies, two different voltages, then automatically I can say the delay will occur if you do this. Delay will occur. So now here the power supply also is required to settle large time measure. To settle large time, the power supply also is required. Next, sometime you might have studied the twin tub process, right? That is a two well, single well, two well, and a triple well. Actually, here with the help of this also we can do a triple well. Actually, the process. The triple well technology also we can use that, but that technology is very complex actually. Triple well technology is very complex because we need to set the multi threshold. So that is what here we seen in this diagram. You can see here. We are showing here like the circuit like clock rate. This will be percentage of clock rate and the percentage of you are seeing. See here, when you are seeing in this two different. One is VDS. This is DVTS. This is a VDS in the sense. What is a VDS? This is nothing but your scaling, power supply scaling. DVTS, dynamic voltage, time scaling. Okay, this is voltage dynamic time scaling actually, this one. VDTS. Now we can see VDS and DVTS. So what happened in VDS actually, as the clock rate reduces or increases, you can see the percentage of it is for your 70 nanometer technology, your VDS will be increases. But at the same time, you can see the DVTS that will get reduces actually is somewhat. You can see the difference. You can able to see the difference. But the very important thing, what about the leakage power? See, if there is no scaling of VDD and VTH. If you are not doing the scaling of VDD and VTH, then even though for that as the clock rate is increases, then the leakage power, see, starting this from it will go. But when you do the scaling, we'll get in this way. That is what we can observe here, the runtime, leakage, power, dissipation. These are the techniques. This is about the leakage power minimization technique for active and ideal in circuits. Next, we'll go for issue is deep submicron design issue. So deep submicron in the sense we know that the L will be less than 250 nanometer. That is what. So when the circuit is goes less than 250 nanometer, then how your circuits will get affected, or how your what are the, when you are going for designing such kind of circuits, what are the design issues will be performed when you are scaling down the feature size, means when you are scaling down the length of the channel, there will be important issue. The important issue is for high performance and high density. The important issue will be these two, okay, in the VLSI cycles. So our some second order effects will become a series for short channel effects. So here what are the things we are going to study means like the short channel effect reduction, which includes the two effect already we studied. Again we are going to see that the short channel effect, that is SEE will say short effect reduction, which includes the first one is threshold voltage Rolloff. Then second one is DIBL. These two will be become the major challenge in deep submicron devices. So what you will do? Let us study the first one, that is short channel threshold voltage Rolloff. First is threshold voltage roll-off. Now here we can see we are showing it's a schematic of a MOS transistor. This is the schematic of MOS transistor. Okay, so this will be for N plus, this is N plus, here substrate is P. Okay, so now here where the L, the capital L, which is showing here, it is nothing but a channel length. Then X, that is Xj, you can see this one. The Xj is Xj is nothing but the source and drain junction depth. Okay, so now here you can see the surface potential of the short channel. Surface potential of the short channel and the long channel devices will be before the strong inversions earlier, like this figure. You can see this figure. So this figure shows that surface potential of short channel and long channel. That is when Vd is equal to 0 volt. Now we can see here in this we are saying the drain gate, that is a Vd is equal to 0. Gate also will be is equal to 0. Sorry, not gate, drain, source and body voltage. All are 0. Then your gate voltage is less than the threshold voltage. Remember, it's in both cases. Okay. So by this case, for long transistor, that is for long channel transistor, the barrier 5B1, this is for long channel. Which one is? This one is long channel. This is short channel. Okay, now you can see for long channel, the 5B1 is constant. You can see here in this diagram only you can see, from that only you can write for long channel the 5B1, that is surface potential, is constant actually. It is constant. Hence the threshold voltage is not sensitive actually here. The VTH is not sensitive. It won't change to the channel variation. But for short channel, what happened? The 5B2 is reduced. You can see that it is reduced along with the scaling. Along with the scaling of channel length, that is L. So therefore, smaller the channel length, you can see this. Smaller the channel length, that will lower the threshold voltage. So L less, then I can say the threshold voltage also will be reduces. So now we can say what is the relationship between these two now? The relationship between these two is the relationship between, we can show the diagram. So this is the relationship between the threshold voltage and the L. Okay, you see from this what we can say, if you want the device has to work properly, if device has to work properly, then your dVTH divided by DL. See from this again, the change in length then will change in the threshold voltage, right? Cannot be too large. That is very important here, the parameters. Okay, if the device has to work properly means then your dVTH, that is a change in the length, will change the threshold voltage. That cannot be too large actually. So this will determine the minimum channel length. The minimum channel length, that is L minimum, is minimum channel length. That is the minimum. See here we go. Okay, so it can't go beyond that minimum channel length. It cannot go beyond the minimum channel length. This is about the VTH roll-off. That is the meaning of roll-off. Now next, let us go for the second. The major important factor is drain induced barrier lowering. That is double, right? Already we studied. That is double. So what is a double actually? So already we studied. So much information is given on based on the double actually. Just to see the figure, we'll get the clear idea. See this. This is your long channel, right? This is the long channel actually. This is for a short channel. The surface potential for long channel and short channel device at larger drain voltage. See the drain voltage, which is that VD is greater than 0. The long or short, if I consider, then the drain, large drain voltage for longer channel devices. So the barrier, which is the barrier here, that is nothing but 5B1, right? The 5B1 is not sensitive to drain voltage for longer device. Then for a short channel device, the barrier will be reduced, that is 5B2 is reduced along with the increase in the drain voltage, which will cause higher subthreshold cost. It causes, which one? Short channel. It causes higher, that is right, higher subthreshold current and lower threshold voltage. You can see this. That is why, so means that initially will be like the VS VB will be is equal to 0. The VS is equal to 0. Bulk voltage also will be 0. then your drain voltage is greater than 0, then your gate voltage is less than Vt. Okay, so now we can see this. What you got? We got as a BA. This is nothing but your surface potential. 5 BA is surface potential, then plus VDD. So now this is about your this actually it's a surface potential for long and short channel device for VD is greater than 0 actually. This is what the drain induced the barrier lowering. So this already we studied. Next is key to minimize short channel effect. How we can minimize the short channel effect? So if you want to minimize the short channel effect, we need to have sufficient larger aspect ratio of the device's network. Okay, so aspect ratio I can say by short AR I can say, or I will write like this. Okay, what is meant by aspect ratio? The aspect ratio is nothing but it's the ratio of length of the channel to width of the channel. Aspect ratio is equal to length of the channel to the width of the channel, or dimension lateral by dimension vertical, or I can say L by W. So for MOSFET, we can express the scaling aspect ratio, that is AR will be is equal to L divided by, because L will be fixed, right? L will be fixed, only W only there. So fixed Tx epsilon Si divided by epsilon x into power 1 by 3 into t to the power 1 by 3 into xj 1 by 3. See, this is the formula for L actually. Where we need to know something over there. It is like epsilon Tx. What is the Tx? The Tx is nothing but it's a oxide thickness. Then epsilon Si, it's a silicon permittivity. Then epsilon ox is oxide permittivity. Then the T is depression depth. Then which is pending xj. The xj is nothing but junction depth. So now from this equation we can see this. I'll consider equation number 2, this equation number 1 you see. Now from this only I can say simple this Tx into is right. So now we can see the reducing the factor, which are the factors we need to reduce it. So very important thing. Important. Reducing Tox D and XJ will reduce the short channel effect. Short channel effect of MOSFET. So these three factors only we have to take care. Oxide thickness, then depletion depth, then X, that is the junction depth. So what we can do, so to minimize short channel effect, the modified structure can be used. The MOSFET modified structure, okay, that is MOSFET modified structure. Okay, let me show the MOSFET modified structure here. See this? You can see that structures here. The structure which is showing here, the structure, this one, like structure A, this shows that schematic of the low impurity. Okay, the low impurity channel, shallow junction, bulk MOSFET. Then this figure actually showing the single gate SOI MOSFET. SOI means silicon oxide insulator. Okay, now we can see in this, see, low impurity channel. Low impurity means this one, P plus plus. The P plus plus or P minus. P plus plus is nothing, it's a high impurity actually. It's a high impurities. This P minus low impurities. Junction depth. You can see the compared to the previous diagram. Here you can see what changes are making. This is your SiO2 layer, silicon dioxide layer. Then the thickness here is the. So here we are using a simple 1P substrate. Then we are using this only, silicon oxide insulator again. Okay, so now the small short channel effect of the transistor is because of the small depletion depth. There's small depletion depth. See this, there will be small depletion depth, under the junction depth. So on this, I can make it as like that. The small short channel effect of this transistor is because of smaller depletion depth, that is D, and a smaller junction depth. Okay, yes, this will be. So now we can write a single gate will be introduced. Already we introduced in that the single gate. That's why I said it is a silicon on insulator. That is SOI, silicon on insulator actually. So that MOSFET we shown the figure. In that sense, since D is equal to xj. See this in this diagram actually. D is equal to xj actually. Okay, so it's in single. D is equal to xj. Then AR will be given, that is aspect ratio is given as L divided by, as you know the formula already, the T arcs into epsilon SI divided by epsilon arcs the whole power 1 by 3. In the previously what was there, that is in the previously we had like this, okay, d power 1 by 3 into xij power 1 by 3, right? So that xj will be d is equal to xj. So I can say again this also d power 1 by 3. So this will become as L divided by T arcs into epsilon Si divided by epsilon arcs the power 1 by 3 into d to the power 2 by 3. This is for single gate, okay. If it is double gate, so let us go for double gate. Double gate silicon on insulator. By short, we can call it as DGSOI MOSFET. So for that diagram you can see this is a double gate actually. This is gate number 1. Okay, this is gate 1. This will be your gate 2, correct? So double gate, top and 2. Gate 2. When I having two different gate, then what will be the aspect ratio? The aspect ratio will be, that is AR is equal to L divided by T arcs into epsilon I divided by epsilon arcs, then the whole power 1 by 3. This will never change, right? Then what happened? Previously it was D by 2, because what happened, that D, the whole total D become half. That is nothing depletion. That is nothing but your depletion depth. Right? That is become by 2. Then again, what about the junction? Junction also become by 2 actually half. That also made of. So it is 1 by 3. Even this also is 1 by 3. So what happened here? It is clear that the effective junction depth and the depletion width are reduced to half. That is what we can see. We can make a note of that. Clearly, the effective junction depth and depletion width are reduced to half. Half of that of a bulk MOSFET. So therefore, the short channel effect of a double gate silicon on insulated MOSFET is smaller than. So from this I can say, therefore, the short channel effect of DGSOI MOSFET is much smaller than the bulk silicon MOSFET. So these two, the short channel threshold voltage Rolloff and the DIBL, are two short channel effects which will complicate those two parameters. Which parameters? One is VTH Rolloff and Dibble. These two parameters only. Okay. So those two parameters will complicate the transistor operation. And it will degrade the performance. So degrade the device performance. So still, if you need to minimize the short channel effect, then what you need to do, you have to use the sufficient larger aspect ratio is required, and some novelty in the mass structure also can be used. So nowadays, just like it has come, not only to like a double gate, it is there. No? So now, so it has come. Presently the using the novel architecture is the FinFETs are used. Currently. So this is all about how we can like how the short channel, what are the techniques, or how you can minimize the short channel effects.